No. Question 2. Prove that one upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 plus and so on plus 1 upon n into n plus 1, that is equal to n upon n plus 1 for each n belongs to n. We have to prove this statement is true for all the natural numbers. Sum of n terms of this kind of series equal to n upon n plus 1. We are going to prove this sum is true for all the natural number n. Here your nth term, you observe for nth term of this series is n into n plus 1. So let given statement is Pn. So Pn can be written as 1 upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 plus and so on plus 1 upon n into n plus 1 equal to n upon n plus 1. Let n equals to 1. P1 denotes sum of one terms. Sum of one term means that is the value of first term. That is the value of first term. So you can write your P1 is equal to 1 by 2. Now you substitute n equal to 1 in its sum. That is equal to 1 upon 1 plus 1. So P1 equals to 1 by 2 equals to 1 by 2, which is true. So we can say that therefore Pn is true for n equals to 1. Now we suppose that Pn is true for n equals to k. N equals to k. So Pk can be written as 1 upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 plus and so on plus kth term becomes, this is 1 upon k into k plus 1 and this sum equal to k upon k plus 1. This is 1. We will prove that Pn is true for n equals to k plus 1. So now you can write your Pk plus 1. You can write your Pk plus 1 equal to Pk means sum of k plus 1 terms equal to sum of k terms plus k plus 1th term. So this is your 2. Now your Pk sum of k terms is equal to k upon k plus 1 and your nth term is, this is 3, your nth term is 1 upon n into n plus 1, so k plus 1th term is 1 upon k plus 1 into k plus 2. So in this way, this is 3 and this is 4. From 3 and 4, we substitute Pk equal to k upon k plus 1 and ak plus 1 equal to 1 upon k plus 1 ak plus 1 equal to 1 upon k plus 1 into k plus 2 in 2. We get, what we get? You can write your this step as Pk plus 1 equal to, your Pk is k upon k plus 1 plus 1 upon k plus 1 into k plus 2. Now you observe the common term in the terms of Pk plus 1. Your common terms is 1 upon k plus 1 and in the bracket this is k plus 1 upon k plus 2. You solve them. 1 upon k plus 1, your LCM is k plus 2 and here k square plus 2k plus 1. So that is equal to 1 upon k plus 1 into k plus 1 whole square upon k plus 2. And when you solve this, one power will be cancelled. So it is your Pk plus 1, your Pk plus 1 is equal to k plus 1 upon k plus 2. Now you go back to Pn. This is your Pn. Now in this statement, when you take n equals to k plus 1, then what happens? Pk plus 1 equal to k plus 1 upon k plus 2. So you can say that which is true. Therefore, Pn is true for n equals to k plus 1. Hence, Pn is true for each n belongs to n. So in this way you are doing questions of this chapter. Here one step is basic step in which you are proving the given statement Pn is true for n equals to 1, and in induction step you assume that Pn is true for n equals to k and you will prove it is also true for n equals to k plus 1. Then by induction property we can say that the given statement is true for all the natural numbers. Now come to next question. Prove by using principle of mathematical induction that question number 3. Prove by using principle of mathematical induction that mathematical induction that 1 plus 3 1 plus 3 square plus 3 cube plus and so on 3 to the power n minus 1. This is equal to 3 to the power n minus 1 by 2 for each n belongs to n. So that is the question. Let given statement is denoted by Pn. So we can write then Pn equals to 1 plus 3 plus 3 square plus 3 cube plus and so on plus 3 to the power n minus 1 equal to 3 to the power n minus 1 by 2. This is 1. Let n equals to 1. This is the basic step in which we are going to prove Pn is true for n equals to 1. So your P1 is the value of first term, and that is same as 3 to the power 1 minus 1 by 2. So your P1 is equal to 1 equal to 2 by 2. So P1 implies that 1 equals to 1, which is true. Therefore, Pn is true for n equals to 1. This is called the basic step. This is your basic step. So now we assume that, now induction step. We assume that Pn is true for n equals to k. This is your assumption. So you can write your Pk equal to 1 plus 3 square plus 3 cube plus and so on plus 3 to the power k equal to 3 to the power k minus 1 equal to 3 to the power k minus 1 by 2. This is the result 2. We will prove that Pn is true for n equals to k plus 1. So now you can write Pk plus 1 equal to Pk plus 1 sum of k plus 1 terms equal to sum of k terms plus k plus 1 at term. This is the third step. Now value of Pk is equal to 3 to the power k minus 1 by 2. This is 4, and your nth term is 3 to the power n minus 1. So your ak plus 1 is equal to 3 to the power k. This is 5. Now substitute Pk equal to 3 to the power k minus 1 by 2 and ak plus 1 equal to 3 to the power k from 4 and 5 in 3. In 3. You leave this. statement. 5, 4 and 5 in 3. So we can write pk plus 1 equal to, your pk is 3 to the power k minus 1 by 2 plus ak plus 1 is 3 to the power k. So you simplify this very carefully because this is very important and we can make the mistake while solving this step. So that is equal to, your LCM is 3, this is 3 to the power k minus 1 plus 2 into 3 to the power k. So when you add 2 into 3 to the power k, 2 into 3 to the power k plus 3 to the power k, when you add them, then what happens? Your 3 to the power k is common. So here you left 2 plus 1 into 3 to the power k. You remember this. So this is 3 to the power 3 into 3 to the power k, and it is equal to 3 to the power k plus 1. So while simplifying this, so you may write this is 3 into 3 to the power k minus 1 by 2. So in this way, this is equal to 3 to the power k plus 1 minus 1 by 2. Now again you reach to 1. So when you take in this step n equals to k plus 1, here your pk plus 1 equal to, substitute n equals to k plus 1, this minus 1 by 2. So this is true, this is true. Therefore, Pn is true for n equals to k plus 1. Hence, Pn is true for all n belongs to n. For all n belongs to n. Now next question. Prove by using principle of mathematical induction. Prove by using principle of mathematical induction that 1 into 3 plus 2 into 3 square plus 3 into 3 cube plus and so on plus n into 3 to the power n, that is equals to 2n minus 1, 3 to the power n plus 1 plus 3 by 4 for each n belongs to n. So when you observe the series, so when here is 1, then this goes as a power of 3 in this term. If here is 2, then this goes as a power of 3. So in this way your series is progressing up to till n terms and their sum is given. Now you have to prove that this sum is true for all natural number. So let Pn is equal to 1 into 3 plus 2 into 3 square plus 3 into 3 cube plus and so on plus n into 3 to the power n. This is the nth term of this series, that is 2n minus 1 3 to the power n plus 1 plus 3 by 4. This is your result number 1. Now let n equals to 1. So your P1 is the value of first term. Value of first term. That is equal to, when you take n equals to 1 here, then it is 2 minus 1, 3 to the power 2 plus 3 by 4. So then what happens? Your P1 is equals to 3. 1 into 3 is 3. It is 1 into 3. That is equals to 1 into 9 plus 3 by 4. So finally your P1 equal to 3, which is true. Therefore you can say that Pn is true for n equals to 1. Therefore Pn is true for n equals to 1. We assume that, now induction method, in the induction step, we assume that Pn is true for n equals to k. So you can write your P of k is equal to 1 into 3 plus 2 into 3 square plus 3 into 3 cube plus and so on plus k into 3 to the power k, that is equal to 2k minus 1, 3 to the power k plus 1 plus 3 upon 4. This is second. We will prove that Pn is true for n equals to k plus 1. True for n equals to k plus 1. So you can write pk plus 1 equal to pk plus k plus 1 atom. This is third. So now you see your pk is obtained from second. Your pk is equal to 2k minus 1 into 3 to the power k plus 1 plus 3 by 4. This is your pk and this is taken as 4. Your nth term an is n into 3 to the power n, and from here your ak plus 1 equal to k plus 1 into 3 to the power k plus 1, this is 5. From 4 and 5 we substitute. From 4 and 5 we substitute pk equal to 2k minus 1 into 3 to the power k plus 1 plus 3 by 4 and ak plus 1 equal to k plus 1 3 to the power k plus 1 in 3. This is 3. So you can write your p of k plus 1 equal to pk is 2k minus 1 into 3 to the power k plus 1 plus 3 by 4 plus ak plus 1 is k plus 1, 3 to the power k plus 1. Again you simplify this term carefully. So p of k plus 1 can be written as, your LCM is 4, here 2k minus 1 into 3 to the power k plus 1 plus 3 plus 4k plus 4 into 3 to the power k plus 1. So when you continue this, so your pk plus 1 can be written as, from these two terms, from here and here, 3 to the power k plus 1 is common, in bracket 2k minus 1 plus 4k plus 4 into 3 to the power k plus 1 plus 3 by 4. So here you can write 6k plus 3 into 3 to the power k plus 1 plus 3 by 4. So when you take 3 common, so you can write 2k plus 1 into 3 to the power k plus 2 plus 3 upon 4. So when you substitute n equals to k plus 1 in 1, when you take here n equals to k plus 1, so pk plus 1, when you take n equal to k plus 1 here, you will get the same terms. So you can write your, which is true for n equals to k plus 1. Hence Pn is true for each n belongs to n. That is the